Welcome to today's Explainer. We're going to totally demystify the incredible physical infrastructure of fiber optics that absolutely powers your daily digital life. If you've ever found yourself wondering how on earth data physically travels across the globe and straight into your living room, well, you are in the exact right place.
Okay, let's jump right in with a super simple question. When you tap a video on your phone, how does that invisible data actually reach you so incredibly fast? Your phone sends a request through your Wi-Fi, and practically in the blink of an eye, the video data travels back to you from some server far, far away. But here's the thing, it doesn't do this by magic. It relies on an actual, physical network made of glass. Today, we're tracing the incredible journey of that signal. We'll start with the magic of light, map out the broader fiber optic journey, walk through the actual steps of bringing that fiber inside, and wrap up with troubleshooting and safety. All right, Section 1, the magic of light. Let's look inside the glass.
So unlike those older copper cables that rely on carrying electricity, fiber optic cables use pure light to transmit data. That's exactly how we get such massive speeds over crazy long distances with barely any signal drop. And all of this happens inside a tiny strand of glass that's literally about the thickness of a human hair. It's got three main parts. Dead center is the core. That's where the actual pulses of light travel. Wrapped around that is the cladding, which traps the light inside. And finally the coating, which is just there to give that fragile glass some much-needed mechanical protection.
Now, you're probably thinking, wait, why doesn't the light just shine right out the sides of the glass? Well, it's all thanks to a really cool physics principle called total internal reflection. Basically, the core has a higher refractive index than the cladding. So if the light shoots in at just the right angle, it's literally forced to bounce perfectly down the core, ricocheting along the inside instead of leaking out. It's an absolutely brilliant piece of physics, and honestly, the modern internet wouldn't exist without it.
Moving right along to Section 2, the fiber optic journey. Let's zoom out a bit.
Okay, so a hugely important term to know here is FTTH, which stands for Fiber to the Home. It means exactly what it says on the tin. The physical optical fiber runs all the way from the internet service provider's network directly into your actual living space. To really wrap our heads around this, let's trace the signal using a really straightforward 5-stage model. Stage 1 is the source. That's the ISP generating the internet service. Stage 2 is transmission, where massive feeder fibers haul that optical signal. Stage 3 is distribution, where splitters divide the signal for individual neighborhoods. Stage 4 is conversion, where a device at your house turns that light back into an electrical connection. And finally, Stage 5, access. That's your router beaming it to your phone or laptop. At the absolute starting line of that whole journey sits the OLT, the optical line terminal. This is a heavy-duty piece of equipment housed miles away at the ISP's central office. You can think of it as the powerhouse of the network. It's blasting out optical signals and managing communications with hundreds of different homes simultaneously.
But how exactly does one line from the OLT serve an entire neighborhood? Well, before it ever reaches your driveway, the signal passes through a fiber splitter. A super common configuration is a 1:32 ratio. That means one single optical beam gets sliced into 32 separate customer connections. And here is the wildest part. These splitters are totally passive. They divide the light perfectly without needing a single drop of electricity out there in the field.
Okay, Section 3, bringing fiber inside. What happens when it reaches your house? The moment that fiber drop cable physically enters your home, it plugs directly into an ONT, or optical network terminal. Now, some providers call it an ONU, but it does the exact same job. It is your internet's ultimate translator. It literally takes those rapid-fire pulses of light and converts them into the standard electrical Ethernet signals that your smart TV, your computer, and your gaming console actually know how to read. Now, a lot of folks get the ONT and the router mixed up, but they handle very different tasks. The ONT is your physical bridge to the global optical fiber network outside. Your router, which plugs into the ONT, is the boss of your local network inside. It handles your Wi-Fi passwords, manages your firewall, and routes the data to your specific devices. Getting all this physically set up takes some serious precision. A technician follows a really strict system. They start with a site survey, pull the drop cable from the street, and then they have to carefully strip and cleave the glass. Next, they do what's called a fusion splice, using an electric arc to permanently weld the glass ends together. After that, they plug it into the ONT and finally set up the local Wi-Fi router. It's a highly delicate operation. Because it's so delicate, technicians live by one golden rule: plan the route before installing the cable. A pro tech is never just going to start yanking cable blindly through your drywall.
They map out the entry points, the distances, any physical hazards, and power sources. All of this is just to ensure they avoid tight bends and don't accidentally shatter the incredibly fragile glass inside the cable.
And honestly, that pre-planning is make or break. You literally cannot treat fiber optic cable like a heavy-duty extension cord. Fiber has a strict minimum bend radius. If you bend it around a sharp corner or pull it into a tight knot, that total internal reflection we talked about earlier completely fails. The light will literally bleed right out the side of the core, or worse, the glass will just snap in half.
Let's move to our final topic, Section 4, Troubleshooting and Safety.
Half the battle in troubleshooting is just figuring out where the problem actually lives. Someone might complain about horribly slow internet and immediately assume the fiber is broken. But a lot of times, it's just a Wi-Fi fault. The actual fiber network outside could be totally pristine, pumping gigabit speeds right to the ONT. But if the local wireless signal is struggling because of thick walls or an outdated router, well, it's going to feel slow.
So if we want to diagnose the ONT itself, we just read the lights on the front. They tell the whole story. Power means it has electricity. PON means it's talking perfectly with the ISP's network. LAN means your router is plugged in. But the big one to watch out for is LOS, loss of signal. If you see that flashing red, there's a physical issue. It means the fiber is broken, a connector is filthy, or a splice has failed.
And speaking of filthy connectors, dirt is basically public enemy number one for fiber optics. Because we're dealing with microscopic light pulses, a single speck of dust can block the signal completely. Techs absolutely cannot just rub a connector on their jeans to clean it. They follow a super strict mantra: inspect the fiber, clean it, inspect it again, and only then do you connect it.
To guarantee everything is perfectly clean and functioning, technicians rely on some incredibly high-tech gear. They use a VFL, or visual fault locator, which blasts a visible red light to expose bad bends. They use optical power meters to check the exact decibel strength of the invisible signal at the house. And they use OTDRs, optical time domain reflectometers. These things are amazing. They shoot pulses of light down the underground cable and can tell you exactly how many miles away a break or a bad splice is located.
But listen, handling this glass and using these tools comes with some very real, unique physical risks. The safety rules are strict. When techs strip and cleave fiber, they create these tiny, invisible shards of glass that can easily get under the skin or into the eyes. Because of that, every single scrap has to be contained immediately, eye protection is non-negotiable, and they always have to use proper personal protective equipment.
Which brings us to the most absolutely crucial, non-negotiable rule in the entire fiber optic industry. Never, ever, look directly into a fiber or a connector. The lasers powering these communication networks are entirely invisible to the human eye. So even if a cable looks completely dark and dead to you, it could be firing intense, invisible laser radiation that will permanently damage your vision before you even know it's happening.
It's honestly mind-blowing when you take a step back and think about it. Our entire digital reality, working from home, streaming movies, scrolling social media, it all completely depends on microscopic beams of light safely racing through miles and miles of fragile glass, right up to the walls of our homes. So the next time a video loads for you instantly, take a second to ask yourself, just how far and how incredibly fast did your light have to travel to reach you today? Thanks for tuning into this explainer, and stay curious.